Hello. Welcome to the YouTube Live. I'm just setting up all the screens right now. Welcome. I see you there in the chats. Nice to have you here. And just gonna set my windows up and then we will get started. As usual, first we will do a share out of our concepts, our ideas for concepts. And don't overthink it. Just flip through the readings for the week and just pick out some things that seem pretty key. Maybe we'll dive deeper into one of those. And then you're going to see, if you look on the YouTube Live page on our Canvas, that after we talk about the concept a little bit, I've got a brainstorm that says, how else can I help you today? And that's a brainstorm, so you can vote up and down. You don't have to actually contribute something to just say, you can just do plus or minus on it. And I want to get I want to get a good idea of what people want to see on here. My second Zoom group talked a lot about feeling the need for more concrete examples, and I can certainly help you with that. I can start that today instead of waiting for Thursday. So if you, while you're flipping through the book and just waiting for us to warm up, if you want to flip through those sections and look at your homework assignment and consider asking me to do one of the homework questions out, I'm happy to do that early in the week, because I know that the people who are watching today are getting going early in the week. And so you're not trying to just get me to do your homework, is what I'm saying, is you're trying to get me to provide resources so that you can learn constructively. And so I definitely want to do that with you. I will just wait to see your requests. So you might want to set up your windows like I'm doing right now, and maybe even open your homework assignment. And I'm going to get my book out. Yeah, so I'll be ready to take your requests, and I'll probably change a couple numbers so it's not exactly the same problem, but it'll definitely build up a resource that's going to help you learn. I want you to feel like you're getting somewhere when you're learning. So if you're feeling like you're stuck in the mud and you just don't get it at all, just ask me specifically about where you're stuck, and we will help to unstick you right away. Okay. Let's see what we got here. Looks like people are still joining. There's 7 results on the poll right now, so I'm going to give it 1 or 2 more minutes for people to join, and then we will get started. Okay. So it's weird. I have more viewers than I have results in the poll. So I guess some people don't want to enter their name into the Who's Here poll. That's totally fine. You don't have to. And you can always log in with an anonymous name if you just want to remain anonymous. That's perfectly all right. I just want to make sure that I gave enough time for those who did want to warm up with the Who's Here poll to enter their name in. It looks like I've got 11 viewers and 8 people who have said hello on the poll. And so if there's nobody else who wants to use that, then I definitely want to move along to the key concepts for the week. And okay, I'm going to do that then. So for everybody who is participating in the polls, if you just go back to that link, you're going to see the new question is, what are some key concepts, as usual? And feel free to throw up to 3 ideas in there. And you see I got the book through, just kind of seeing what we think are some real important things that got introduced this week. And then when I see maybe a common theme arise on the word cloud, then I'll make the next question about to explain that concept in our own words. So I see the word power getting really big on the word cloud, and that's cool. I feel like you're talking about the power rule, and I just want to remind people that when we do the word cloud format, that's the one format where you have to combine more than one word with an underscore. Otherwise, the words will get broken up. So I think that the word power is really big, but power rule is not the thing that's really big because people maybe forgot to put the underscore. No problem. I can see what you mean there. So yeah, our big ideas here are integration, and integrations are kind of tied to the concept of Riemann sums, similar to the way that we integrate a state equation to get a trajectory, and the way that we integrate state equations is with the Euler's method. That's pretty much the same thing that you're seeing when they're explaining Riemann sums in the book. And then we have that power rule, and that's a big player. And yeah, derivatives and antiderivatives. Yeah. So we can talk about all that stuff. And it really seems like, strangely enough, I feel like integration might be winning this contest. It seems like there's kind of a two big themes, and one is like the derivative rules, particularly the power rule that people might be practicing on power functions right now, and then there's integration. Now integration and differentiation are okay, sorry, I was just getting a message from someone. uh yeah, integration and derivation are kind of the opposite of each other. And so if you have a function and you take its derivative and then you integrate the derivative, you will come back to the original function that you started with. It's kind of like what we learned about inverses in pre-calculus, where you can like do an operation, and then if you want to take that operation back, you have to do the inverse of it. And differentiation and integration are related similarly, that they kind of cancel each other out. And that connection between those two processes is known as the fundamental theorem of calculus. So you're going to see the FTC, the fundamental theorem of calculus, in a video on my optional playlist for this week. I didn't want to make you dive into too many concepts too deeply because we are learning so many new things this week. So there's the kind of required playlist for week 5. And then for people who are ready to take on more and who want a deeper dive, then there's the optional playlist where I kind of go through more of the rules that I didn't assign problems on. And that was just to make sure that the learning this week felt manageable to you, and also that it stays tied in with what we're really after, which is how to do mathematical modeling. So just to be transparent, you're not getting a full delivery of like a normal calculus course here. That's why you're going to see just a handful of credits offered in Calculus 1/2, whereas somebody who would usually go through the whole gauntlet of calculus, that would be 4 credits of Calc 1, 4 credits of Calc 2, 4 credits of Calc 3, 4 credits of Calc 4 even, and then the person might move on to mathematical modeling. So we kind of, we're not keeping it all a secret, but we're not asking you to go like too deep into the calculus, because there's a lot you can understand about mathematical models without having to know the ins and outs of all those rules. Somebody's chatting with me on the live chat, so I'm just going to respond to that, and then we're going to pick out one of these things to go deeper into in just a second. So hopefully everybody who wants to work with the polls is able to. I just want to remind everyone that if you want to engage in the polls, then the link to the poll, the polling link is up there on the page. It's called Live Poll Questions link. And then if you want to see the results, you have to go back to the Canvas page. And today's date is April 28th. So make sure that you're on the YouTube Live 428 page. We do 2 of these a week, so there's a lot of pages that say YouTube Live, but you got to make sure that during the live event that you're on the actual live page for the day. Otherwise, you're not going to be able to see the poll results, even though the link is the same. And so you might be like thinking that you're interacting but not seeing the results. That could be an issue. Okay, hopefully that's corrected for everybody. And so now we've got 2 major big words here on the word cloud. One of them is powers and the power rules and the derivative rules, and then the other one's integration. And so maybe the power rule is just a rule, and I can certainly talk about that. I can definitely go into the power rule maybe when we start to ask for more concrete examples, but I don't think that's going to be as valuable to share as a concept as integration is, because integration, kind of like last week how derivation was a huge concept that we were introduced to, for this week integration is again like a really foundational and really big idea concept. And so I'm going to pick integration for our next question that says, what is integration in your own words and what are your questions about it? And so now I'm going to move over to that and ask people to put in their explanations and also their questions. So I'm trying to evolve the way that I help you during the YouTube Live, and kind of going off of what's happened in previous sessions. I used to just ask you to explain it or to give an example, but I heard a lot of people saying, the book doesn't give me enough examples, and I don't know where to find the correct examples. So I'm not really asking you for an example right now. I'm just going to ask you to explain it in your own words. And then if you have questions on it, ask me your questions, and then I can give examples too. That way everybody feels like they've got enough there so that they know what they're shooting for when they're trying to learn this stuff. Right. Okay. So go ahead and enter anything you want to say about what integration is in your own words. And while you're doing that, because that takes a little while for everybody to enter it, I'm actually going to write the power rule up there because I saw. Oh no, you don't need to enter any underscores. So the underscores to connect more than one word are just for the word clouds. And what poll I have up right now is called the open-ended scrolling. So you can just type in as long of an explanation as you want. You don't need to use the underscores. And if you don't want to explain it, but you have a question about it, you can also put the question in there. Yeah, so some people are saying like finding f of x starting with the derivative, right? So if we have the derivative of a function and we want to know what that function actually was, we have to integrate it back up to figure out what the function was. Someone else has said integration is the inverse of the derivative, which means you're trying to undo the derivative and return to the approximate original function. Yeah, exactly. All the information found that is specific to a particular integral and the function of the derivative, integrating the first function with the second, which is the change. Yeah, so thanks for contributing those ideas. And also, if you have any questions related to integration, go ahead and throw them in there too. Let me go through a concrete example, and I'd also really appreciate it if you could give me some feedback on the legibility of what I write on the board. If you can't read it, I'll move everything closer, but it's better to be able to show both boards at once if we're able to do that. So just let me know. Hopefully the quality stays good, but let me know. And I'm going to go through an example of how derivation and integration are related, and I'm also going to use the power rule. So I'm going to do this example on a power function because I saw so many people put that into the word cloud too. Okay. Okay, so I just wrote something on the board there as a test. Hopefully you find that readable. This is an example of how derivatives and integrals are related, and I'm going to use a power function for this example so that we can apply the power rule. And then maybe we'll talk about the graphs too, because somebody's referencing figure 2.5.1. So let me take a look at that figure and see if I can build that into the example here. So I'm just going to look at figure 2.5.1 really quick and see how that all ties in. Oh, I think that maybe you meant exercise 2.5.1, not figure. Yeah, probably did. So yeah, this is totally related to this. You see, this is like the first assignment for this week is matching up these graphs. And so let's definitely build that into the example to help you with exercise 2.5.1. Okay, so just as a very beginning example, I'm just going to use a really classic function that's easy to work with, which is that, let's say that, actually, I don't want to call it f of x. I'll just say, I'm just going to name the function, okay? So let's just say that we have an example, y is equal to x squared, right? That's just such a classic example of a power function here. And if I wanted to take the derivative, so y prime, which is also called dy dx, because this is a function in which the input variable is the base and the power is just a specific number, it's a fixed power, what the power rule says is that when you take the derivative of a term like this, of a function like this, you take the power and you bring it down in front of the x. So here we have x to the 2, and the first step is we're going to take the 2 that was up there, and we're going to bring it down in front of the x. And then the second step is you're going to rewrite the base x, and then you're going to raise it to a power which is 1 lower than the power that you had before. So that's why I have x to the 1, or 2x. Okay, thanks. Unfortunately, people are saying the board's blurry, so yes, let me do the thing I did before. That will help you. Same here, but I wasn't sure if it was just for me. It gets better once Melissa is done moving back and forth. Yeah, okay. I think it does have to do, I really tried to troubleshoot what the issue was. And I think it does have to do with me coming back and forth towards the camera. But also, hold on, there's this weird light that I'm using to light up the room behind my screen. I'm going to remove that light because I think it might be interfering with the Wi-Fi on my computer, because it's like a, if you want to see, I have this light that I stole from my chickens. And does anybody recognize that as that's a warming light for baby chicks? And it does light up the room, but I think it might also interfere with my Wi-Fi. So I'm going to remove that, see if that helps. Kind of put that over to the side somewhere. I hope that helps if I put it up there. Okay. How's that? Is that better? Hopefully that seems like it's better. And then the other thing you're seeing is just the glare from my computer. So if I turn down my computer glare and I put it like that, thank you for communicating with me to tell me that was hard to read. And hopefully it seems better, although, just put this up a little bit. Okay. I don't know, much better. Okay, that's great. Oh, this light is about to fall off that way, so let me try a different strategy with the light. Sorry that I have to do this in front of everybody, but that light's about to fall down. So let's see what I can put this on. Okay. Does that seem okay? I know there's a little bit of glare there, but hopefully that helps it to be readable for you. And so what we're trying to do here is we're trying to explain the power rule, which is a rule that tells you how to take the derivative of a power of a function in a power term. Okay, great. Yeah, it's working for me too. Yeah, I moved it out of my face. Thanks. So hopefully everybody sees what I mean when I'm saying that if my term is x to the squared, then I take the squared for the power rule. When I take the derivative, the 2 that was up here goes in front of the term, and then the x is now raised to the first power, and this 1 comes from the fact that this used to be a 2, and 2 minus 1 is 1. Okay, so this coefficient goes in front, and then the power gets lowered by 1 right here. Okay, cool. So let's just try that again to make sure that everybody understands this more generally. So I'm going to erase the work that I did before, and you tell me, what do you think the derivative of x to the 4 is? Using the same rule and the same method that we had before, go ahead and throw it into the cup here. I'm just doing a check with the people who are participating. Can anybody tell me what they think the derivative for x to the 4 is instead of x squared? It's the same format because we have a base, which is x. The x is in the base. And then the power is 4. So somebody has put in the polls 3. And there is going to be a 3 in the answer. But where does that 3 go? Exactly, right. So the 4 that used to be in the exponent jumps down in front, and so the 4 is now multiplying the term. And what happens to the x is instead of being raised to the 4, it's now raised to the 3 instead. Exactly. Great. So you're all getting that idea. That's really key, and it actually describes a lot of what's happening here when we do derivatives and then back up to integrals when we're working with polynomial forms. Because if you recall from pre-calculus, polynomials are combinations of a bunch of different terms like this, where all the powers are positive whole numbers, right? And so we can actually now take the derivative of all sorts of polynomials when we combine this power rule with the properties of linearity, which allow us to take derivatives of sums and take derivatives when there's a constant multiple in front. Taking the derivative, the action of taking the ddx on something is actually a linear operator. And that is really important to the fundamental theory of differential equations, particularly if I was going to derive analytic forms for solutions to the equations. I have to use the fact that differentiation and integration are both linear operators. I have to use that fact a lot. Okay, so to try to explain that a little bit, what I mean is that when I'm taking the derivative, I'm taking the function y and I'm acting on it with a differential operator, which is called d dx. So I know that I had written that it's dy dx. That's what I'm doing when I'm talking about y prime. But you can also see it this way, which is that I'm acting on y by doing the action of differentiation. And this part here, d dx, is called a differential operator. And so how I would say that in plain English, I could say I'm differentiating the function y, or you could just say y prime. I'm just taking the y prime. Okay, and so you can see that on a polynomial term, on a power term, it takes it down a notch when I take the derivative. But then if I want to get back to what I had before, then I have to integrate it back up. So I'm going to do that on this side of the board here. So I'll just turn it a little bit here. So now I'm going to integrate to return to the original function. Okay, and I don't know if you can see all of that. Yeah, so now I'm going to take the integral. You see how I went from here downwards to take the derivative? So what I'm going to do next is I'm going to take this derivative, y prime is equal to 4x cubed. And what they're teaching you in section 2.6 is they're teaching you how to go back to the original function when you know what the derivative of the function is. Okay, and the notation for that is integrating. Yeah, taking y prime is taking the derivative. Yes, yes. So when I wrote this y prime down here, I was taking the derivative of y. And then so over here, I have the derivative. And let's say that we're in this situation. Now, when we return to the world of mathematical modeling, we're going to be in the situation where we know the derivative and we don't know the original function. That's what our state equation is trying to say. Because remember in chapter 1, we formed a lot of equations that said like x prime is equal to this or that. So y prime is equal to this, but what's the original y? In terms of what we're doing in modeling, that's going to be like, here's my state equation, but what's my original function? What's my solution? Or what's my trajectory? What does the state equation predict about the behavior of the function overall? That's why we need the backwards operation of integration is to reverse the process of differentiation that we have for the state equation. So a lot of times that's written as an elongated S sign. So that thing I just wrote there is an integral. And where this funny looking thing comes from is the fact that an integral conceptually is in an infinitesimal sum. That's what they're explaining with the Riemann sums. And so you have this summing kind of behavior. And so this actually came from using S for sum, but like just stretching it out into this elongated thing, which is called an integral. And so I'm going to integrate up the y prime. And actually, since y prime is equal to 4x cubed, I'll just write that I'm going to integrate 4x cubed. And then usually, just like how I start the statement of integration with this elongated integral sign, it's kind of like a set of parentheses where this is the start of it. This is the thing that I'm integrating, and then this dx over here is the end of it. That's like the closed parentheses. So the thing that is between the integral and the dx is the thing that I'm integrating. And what this math here says is what kind of function would ever give you this 4x cubed for its derivative? And that's what we just learned over here with the power rule, is the kind of function that's going to give me 4x cubed is x to the fourth power. So the answer to what's the integral of 4x cubed dx is x to the fourth power. So that's how integration and differentiation are related. There's a little bit of something extra, though, that I'm not telling you yet here, where this isn't the only answer that I can get. There's actually going to be more answers than this. And so this might be a little check-in to see if anybody has read this far. I don't know if anybody's going to be able to get this detail yet. You'll probably learn this as you read section 2.6 very carefully. But does anybody know what's missing here when I say x to the fourth is not the only thing that would have its derivative be equal to 4x cubed? There's actually a whole bunch of different functions that all have the same derivative. Plus c, right, yeah, there's a plus c term. So now I want to explain the plus c term. I was holding off on that at first, but now I'm going to add in the truth of it, which is that instead of just calling this y is equal to x to the fourth, let me say that this is called x to the fourth plus a constant. Okay, and so what I mean is that this is the quartic function x to the fourth, and it's vertically translated by this constant function. So you can think about the picture x to the fourth being raised or lowered according to whether the value of plus c is a positive or negative number, right? So now I have this whole family of functions, x to the fourth power plus whatever constant I choose. The thing about constant functions is their derivative is always 0. And that's because they're not changing at all. That's the whole thing about a constant, is that it's constant. It never changes. I'm going to put it over here so you can see a picture of what I mean. Okay, so constant functions. Constant functions look like this. They're just a flat line. They never move. They never change at all. And so if you ask me to look at this flat line and try to draw a tangent to it, it would be really hard to, because it's so flat. But if I did have to draw a tangent to this, I suppose it would be a horizontal line. And a horizontal line has 0 for the slope, which is saying the same thing. It's saying that it doesn't change. There's no change on a constant function. There's no change. Okay, so because there's no change on a constant function, that means that the derivative of a constant function is always going to be 0. Okay, so I'm going to write that underneath the statement no change, because that's really what I'm trying to say, is that if I have f of x is just equal to c, then the d dx of that function c is just 0. There's absolutely no change on a constant function. And so if I add that component to the function I was talking about before, if I add a plus c, then the derivative of the plus c term is just 0. Okay, so I could emphasize that by saying the derivative is 4x cubed from the x4th term plus 0, because the derivative of the plus c is just 0. I could put that in there, but why bother? Because adding plus 0 to something doesn't do anything. So that's why usually that's just left out. But where that comes into play is that when we're going for the integral, right? So when we're trying to reverse the operation of differentiation, and we're going to say, what kind of function would have given me this for the derivative? This is not the only function that would have done that. There's a whole family of functions out there that could have done that. It's this term, which yielded this for the derivative, and then plus c, where c is any constant. So I could have vertically translated that graph up or down as much as I wanted to, and adding or subtracting that constant amount would not have changed the slope on the tangent lines. It would have been the same exact function. And so this happens every time you take an integral. This is a big issue for integrating, is that when you know what a derivative is, and then you ask where could that have come from, the answer is never unique. The answer is not going to be just one exact function. It's always going to be a family of functions. And that family is created by adding the plus constant. Okay, so hopefully that helps you a little bit. Now, let's look at a geometric picture of what all I've been talking about. And that's going to help you with the exercise 2.5.1. Actually, I won't move this. I'm just going to erase what's on the board here, and then we're going to draw a picture. Okay, so one thing I want to mention about this week is that on the weekly schedule page, I put this little link to a Desmos activity, or it might be in the homework actually. Let's see if that helps. Okay, so I put a link to a Desmos activity where when you click on it, it has a function, and it's graphing the function, and it's graphing the function's derivative. What I'm going to do right now is I'm going to draw pictures of functions, and then I'm going to draw what their derivative would look like. And so you can also use that Desmos activity to explore what a function compared to its derivative looks like. And then you can use that on these questions. Actually, since I know that you're all asking for lots of help specifically on homework, I'm going to do this to the homework problem right now. Okay, so I'm going to do what I'm saying and address 2.5.1. Okay, so in 2.5.1 here, we have a bunch of different functions along the first row that are denoted as f. And then we have a bunch of different functions that are denoted as f prime. Okay, and the idea is that you're supposed to match them up. So on the first one that's done for you, this first one, I'm just going to talk through why that function got matched up with that derivative. Okay, because the first function that they show is just a line. Right? That's some sort of function. That function number one is a line. So it has the form y is equal to mx plus b. Right? And it looks like from the picture that the slope is positive, the m is greater than 0, and that the y-intercept right here is a number that's less than 0. We don't have to put actual numbers on it to talk about what its derivative probably looks like, right? Now, let's just practice the rule that we just talked about, which is the power rule, because if I take the y prime on this, so the m is just a constant multiple. So if you see an m in front of an x, that m is going to remain right where it is. But if you take the derivative of this, x to the first power right here, and you do the power rule on it, what it says to do is take the 1 that's in the exponent, x to the first power, and bring the 1 down in front. So I'm going to put the 1 down in front. And then it says to leave the base where it is as x, but then subtract 1 from the exponent. So when you subtract 1 from the x to the 1, you get x to the 0. Right? And then we just talked about how plus a constant, the constant disappears. And so whether I call that constant C or B or whatever it is, the fact of the matter is that this is a constant. And so the derivative of this constant term is just going to be plus 0. So this 0 here is what happened to the B. And this m times 1 times x to the 0 is what happened to the mx term. But just like every other number, x to the 0 is 1. Just like 5 to the 0 is 1 and e to the 0 is 1, every number to raise to the 0 power is equal to 1. And so x to the 0 itself is 1, and it's getting times by 1. So this is just 1 times 1 in here. So what we really have for the derivative is the constant value m. So y prime on a line is m, the slope. And that actually should match up really well with what you learned last week, because when we talked about geometrically, this is a line. So if I was going to try to draw a tangent line to a line, I would just be drawing the same line. There's no other way around it. It's just a line. And then the derivative is the slope of the tangent line. And that's what this is saying right here. The derivative is the slope of the line that you had before. Okay, so the derivative is just m there. And what does that look like? Well, that's just the graph of a constant. You see, if I was going to graph a function m, where m is a positive number, I would just be straight across graphing the function m, where here, this is the value m right there, right? So this is a graph of y prime. So if this is a graph of y, that's a graph of y prime. And that's what they meant in exercise 2.5.1, where they're connecting those two graphs with a red line. That's how they knew that. But let's try to do this to some other functions so that we can really understand how derivatives of functions compare with what they look like. Okay, so I want to make sure I get as much interaction here as possible. So there's 4 more functions in this exercise. Does anybody want me to pick one of these in particular? Like, do you want to see number 2, 3, 4, or 5? So if you have a request for which one you want me to do on the board right now, go ahead and type it into the poll. And then I will look for that, and I'll do that one. Number 2. Okay, sure, that's easy. So now we're going to move on to number 2. And number 2 here looks like, to me, it looks like a parabola with its vertex right over the y-axis there. Just to be a stickler, it looks like that, right? So this looks like a parabola. And that has the form y is equal to x squared. I can tell that it's a y is equal to x squared form because the vertex is located right at 0. And then I know that it's raised above the x-axis. So this is an example where I have maybe like a plus 3 or something. I don't know. Like if this height right here was equal to 3, it doesn't actually say that in the book, but just to guess, if that was a 3 there where its vertex is, then the actual equation for that function number 2 would be y is equal to x squared plus 3. Okay, and so why don't we, and I can do the rest of them too, because I see other people asking for the other ones. So I can definitely do that too, but why don't you practice taking the derivative according to the power rule? So we're gonna do the algebra and we're gonna do the geometry at the same time so you can see it in both of those ways. Okay, so what do you think the derivative is gonna be? What's the y prime? If the y is equal to x squared, so there's the x squared term we talked about before, and then plus 3, and the plus 3 is like an example of a plus c, where this constant is equal to 3 in particular. What do you think the y prime is? Can we say then that y prime is equal to 2, right? You bring the 2 down, and then x to the first power, and then plus a 0. Exactly, right. So now you're starting to get useful, getting more accustomed and used to the power rule. That's great. The 2 came down to go in front. The 1 comes from the fact that it's 2 minus 1, which is 1. And the plus 3, that's a constant, so that differentiates into a 0. Okay, and so that is usually expressed in a more simple way to just say y is equal to 2x. Okay, and what does that look like? Y is equal to 2x. If I was going to draw a graph of this, how would I graph y prime? On this lower axis here, it's just a line. It's a line with a slope of 2 and a y-intercept of 1. And so it's a line that looks like that. And so you can see on the question here that on the bottom row where it says f prime, that very first function on the bottom row is a line that's going through 0, 0. And, well, I can't tell because there's no axes text, but it probably has a slope of 2, which is matching the quadratic form that we started with. So this part here, where we did the power rule, that's kind of the algebra of derivatives. And how that would tie in with the algebra of integrals is that if I took the integral of 2x dx, that, oh, sorry, that's kind of, there's not enough space for the answer there, but what I was saying is how that ties in with integrals over here, I'll use this board over here, is that if my derivative is equal to 2x, right? Because I just showing you how there's a derivative of 2x. If I just knew, if all I knew was that the derivative was 2x and I didn't know what function it came from, that's where I would take the integral so that I could reverse the process of differentiation. So I would take the integral of 2x dx, and I would come to the answer of x squared plus c. Now, when I go backwards on it and I go from integral back up to derivative, integral back up to original function, I don't know what the plus c is anymore, because when I took the derivative, this could have been a plus 3 or a plus 5 or a plus 8. It could have been a plus anything. Its derivative is 0. So when I only know the derivative and I don't know the original function, all I can tell you is where this power term came from, but I don't know what plus what it was. So you kind of lose a little bit of information when you integrate. When you take a derivative, you lose the information of what the constant was. And then when you erase that using the integration process, all you can say is plus c. When we take this back to mathematical modeling and apply it to differential equations, this plus c term is going to be related to the initial condition. So just to tie it in again with what we were learning before, remember when we had all those fun state spaces and we talked about how trajectories, like you click somewhere and then a trajectory shows up? Well, where you decided to click is the initial condition, and the initial condition is going to be related to the plus c here. So it's kind of saying the same thing as that a state equation has many different solutions, and all of those solutions are defined by where you started. They're defined by the initial condition. Okay, so That's, again, a review of derivatives and integrals and how they're related. But what about the pictures? Let's talk about how the pictures are related here. Okay, we started with a picture of a parabola. And what I'm going to do is I'm going to use my red pen and I'm going to draw some tangent lines on that parabola. And then I'm going to think about what the slope of those tangent lines are and show you that if I graphed the values of all the slopes, I would end up with this picture. Because that's the point of the exercise 2.5.1 is to recognize what this type of graph would look like. Okay, so on this parabola, let's say I'm over here and I drew a tangent line. Like if I tried to draw a tangent line at this point right here, it would probably look like this red line, which has a negative slope, right? So if I chose this value of x right here, and then I tried to match up the axes on both of these graphs, at that point right there, I have a tangent line with a negative slope. That's why I'm graphing a negative number right here for the derivative. The derivative is negative because of the negative slope on the tangent line here. And then if I move over a little bit more, like to this position right here, you'll see that the tangent line here, again, it has a negative slope right here, but it has a less negative slope. So it's not as steeply negative as this part when I move to here, okay? And so then if I matched up what the derivative would look like on the graph right here, it would be a negative number, but it wouldn't be as negative as the number I had before because this tangent line is steeper going down, so it has a more negative number for its derivative, and this one is shallower here, so it has a less negative number. Hopefully that's making sense, but if it's not or you have a question, just throw it into the chat thing that we have here about integration. Okay, so I'm going to move along the line a little bit more. And right here where this is bottomed out, at this bottoming out point, at this vertex, if I tried to draw a tangent line, that tangent line would be horizontal because that's the bottom out point. So that's a flat horizontal tangent line. And a flat horizontal line would have a slope of 0. And so that's why the derivative goes through 0 right there, is because the bottoming out or vertex point occurs right there. So there's horizontal tangency, a 0 slope tangency. And then if I move more to the right, and maybe I pick this point over here, which has a tangent line like that, now I'm starting to get positive values for my tangent lines. And so if I drop that down and follow that down to where it would be on here, you're going to see that output for the derivative, which expresses the slope of this line, that's a positive number. So when you take the derivative of a parabola, it always becomes a line. And from what we know about pre-calculus, this is a second order or second degree polynomial, and it differentiates into a first order or first degree polynomial. And that's just a general rule. That's true about all parabolas have derivatives that look like lines. And what we just saw from the previous example was that all lines have derivatives that look like a constant function. And so this is another thing that the power rule is trying to tell you, is that every time you take the derivative of a polynomial, it goes down by 1 degree, by 1 order. Okay, hopefully that's working. I'm going to go through the same question. I'm going to go through 3 and 5. But what I'm going to do for the chats is I'm going to turn on the brainstorm, because after I'm done with this example, I would like to know what other things I can do to help you out today. So I'm just going to let this brainstorm poll go. And for those who are watching and still participating, please think about what else you might want to see me do today after I finish up with functions number 3 and 5 from this. You said all parabolas have a derivative as a line. That's right. Every single parabola that you could ever name is always going to differentiate into a line. You're not convinced. I love it. I love it. I will convince you right now. Thank you for saying that. Okay. This is great. Yeah, you got to be skeptical. That's healthy, right? That's where science comes from, is like, I don't believe you. You need to prove that for me. Okay, so let's see how much you remember from pre-calculus. When we talked about parabolas, they were also called quadratics. So parabolas is usually the name that we give to the graph, but those are also known as quadratics in pre-calculus, right? And one way to express a general form for a quadratic is y is equal to ax squared plus bx plus c. Okay, hopefully that seems familiar. Somebody's saying, what if a parabola is second degree general function of x and y? And that's an excellent question. But if the function I'm talking about is a function of x and y, then it's not appropriate for what we're doing here. Right now, we're talking about functions of a single variable only. We're not going to go into functions of more than one variable. And so we're only going to have x as the independent variable here. And so even if the axis is oblique, even if this is a parabola that somehow kind of turns on itself a little bit, we're going to be talking about this functional form for now. So if you have something that looks like a parabola with kind of an oblique axis, that doesn't obey this form. There's a little bit of a rational term on there, and so we're not going to go into that right now, okay? But what we're going to concentrate on is quadratics of the classical quadratic form here. And so if I want to take the derivative of this, I invite you all to practice right now. Go ahead and use what we just learned about for the power rule to take the derivative of each one of these terms separately. Okay, so take the derivative of ax squared, take the derivative of bx, and take the derivative of plus c, and see what you get for y prime. Okay, and so what we're going to do here is the derivative of x squared is 2x, right? So if there's an a multiplying in the front, we're just going to have 2ax for the derivative of that first term. I wonder if that's confusing. So let me write it again this other way, where we're talking about the constant a just being present in the front, and then the derivative of x squared is 2x. That's where I got the 2ax, is I just toggled the 2 and the a, right? And then the derivative of bx is just b, and that's times 1 times x to the 0. Remember how we talked about this x to the 1 going down to a constant term of just 1? And so that's why we get that the y prime is equal to 2ax plus b. Okay, and so that's when I said all parabolas have a derivative that is a line, because hopefully you kind of recognize this as a functional form of a line, where this right here is the slope m, and then there's x, and well, lo and behold, it even says plus b like we're used to, mx plus b. Yeah, so that is general, the fact that parabolas always differentiate into a line, but it doesn't even stop there. The power rule is so general, it says that cubics will always differentiate into a quadratic, and that quartics, so polynomials of the fourth power, will always differentiate into cubics of the third power. So polynomials always differentiate into another polynomial, which is one order lower than what you started with. Okay, so back to the example from the book here that we're going through. And so what we're going to do here is we're going to talk about number 3, which actually looks like a cubic. Okay, so let's go into the cubic one. And if you're participating in the live polls right now, actually, okay, so I'm going to change it over to the chat box that I'm going to leave open for the live polling. And I would invite you to guess, if you have the book and you're reading along with me, what is the answer for number 3? So function number 3 there, that looks like a cubic. Which letter, A, B, C, or D, or E, do you think its derivative is? Okay, and then I'll draw it on the board. I'll explain it out. I'll do the same for number 5, and then I'll touch on some of the brainstorm requests that I'm seeing on the polls there. Okay, so cubic form, right? So let's move up another higher power where number 3 looks like this. Okay, so this is a cubic form. Cubic form. And the cubic form is always going to differentiate into a parabolic form. Now, when I see a function like this, if somebody asks me to try to draw what the derivative is going to look like, there's always a very easy place that you should always start. And that's going to be with the peaks and the troughs. Okay? Because as I mentioned in one of my videos, yeah, people are saying it's B. Yeah, you got it. You got it. So let's talk about why the answer is B, which is a parabola that you see. And for that, we're going to start with the peaks and troughs. Peaks and troughs always have their derivative equal to 0. Don't believe me? Let's draw a horizontal tangent there so you can see what I mean. You see this peak right here? If I tried to draw a tangent line right at this peak, I would end up with a horizontal line. And the slope on a horizontal line is 0. So that means if I was going to try to write what the derivative was right there, the derivative must go through 0 right there. Because the slope at the point of relative maxima, the slope on the tangent line is 0. And that's the same thing for relative minima. So you can see down here, I've got this trough right here. And if I tried to draw a tangent line directly at that trough, what's going to happen is the slope's going to be 0 because it's a horizontal line. So I'm marking in red down here what are some values that I know about the derivative. Okay? Now, if I marked off these 2 zeros, it actually cuts up the rest of the derivatives into 2 categories. If your derivative's not 0, if you're not at a horizontal tangent, then either you're going to have a positive tangent or you're going to have a negative tangent. Like either you're going to be in a situation like I am over here, where tangent lines have a positive slope. You see all these positive slopes? And if that's the case, the derivative will be positively valued in that part of the graph. In between the peak and the trough, I have a place where the function is decreasing. And so if I draw some tangent lines here, I have negative tangent lines all over the place, tangent lines with negative slopes in between the peak and the trough. And so how I would express that on the graph of the derivative is that all of these slopes are coming out negative between these 2 spots. And then when we go back here, you see the function's increasing again. And so all the tangent lines would be positive in this region. And so that's why I'm getting positive output on my derivative. And so that's why the answer is B, like you're all saying. Good job. Hopefully you're starting to understand exactly why the derivative looks like this when the function looks like that. We're going to try one more time, and then I'm going to go to some of the other requests that I see on the live poll. Okay, so the last one somebody asked me for was number 5. And so another kind of fun way for interaction will be for you to tell me what function do you think is being graphed there for number 5. Here's a picture of number 5. And from what you know in pre-calculus, what kind of function do you think that is a graph of? Like, do you think that's a quadratic or a rational or a logarithm, or what? How would you describe that? I'm going to give you a chance to respond in the live chat there. Like that number 5, I'll draw it on the board here. Number 5 looks like this. It's going up quite fast over here. And in this region, it looks like it's approaching 0, but it never quite touches 0. So this is kind of what I was saying about the Desmos link that I provided on the Canvas page, is that if you wanted to check out a Desmos link that shows you a graph of a function and its derivative, if you had this type of function, you would need to know what you want to enter into the f of x is equal to what. Like, let's say I want to reproduce this graph on Desmos. It's an exponential. Exactly, right. So what's a suggestion for what function I could type into Desmos if I wanted to actually recreate this graph? because I have a link on there on Desmos where you can type in a function and then it'll automatically give you a graph of its derivative as well. So can anyone give me an example of an exponential in its functional form? Like what would I type algebraically here? There's a lot of different answers that could be the right answer. I won't tell you what base to use, but I'll just look to see what you, right, e to the x, exactly. That's just if you wanted base e, or it could be 2 to the x or 3 to the x. It's something to the x where the thing to the x is a number greater than 1, because when we're in the case of exponential growth, right? So it could have been 4 to the x, exactly. Any kind of base greater than 1 to the x. That's the original function. And if you look in section 2.5 in the derivative rules, the derivative of e to the x is e to the x. And that's really magical. That makes it a really special function. And that's what makes it a solution to the state equation x prime is equal to x. I say that in one of the videos in this week's playlist, so you can go there to see more. But yeah, if f is equal to e to the x, then the f prime is also magically equal to the same exact thing, which is e to the x. Okay, and so when you try to match that up, again, to go back to the geometry, what I'm trying to do here on this graph of y prime, or f prime, I'm calling it, is I'm trying to express values of the slope of the tangent line at various points. Okay, so maybe just starting right here at the y-intercept, the tangent line at the y-intercept looks like it has some kind of positive slope. I don't know, it's about this much. And then as I move to the right, it looks like tangent lines are getting slopes that are higher and steeper. Every time I move to the right, I get a tangent line that has a steeper, and steeper slope. And so that's why the graph says your slope is getting steeper and steeper. And it actually is getting steeper in an exponential way, the same exact way that the function itself was going up. And then over to the left, you see the tangent lines as I move away from the y-axis towards minus infinity, is the tangent lines are getting more and more shallow, but they are still always positive. They're never pointing down. They're still pointing up. And so that's why the slopes on the tangent lines are lower, but they're approaching 0, but then they never hit 0. So that's kind of a graphical, intuitive reason why the derivative of an exponential function is another exponential function. And that is going to be a really, really important property as we go back to study state equations again. And so you'll see that it has its own section, section 2.7. Okay. Hopefully that was helpful. Let me see what other things people are curious about. So I have a request for further exercise 2.5, number 4, and then 2.5, number 10, part C. How do we differentiate that? And then 2.6.2. Okay, great. Those are all really great questions, and I can definitely tackle all of those right now. I think that what I'm going to do first is I'm going to tackle the more simpler ones, and then I'll finish by tackling the further exercise from 2.5 and the integration equation question from 2.6. So we're going to start with 2.5.10 because that's a great warm-up to get us started. And we're just going to talk about the function there in 2.5.10 that has a fractional power. In part C, it says differentiate. So this is 2.5.10 part C. This is differentiate f of x is equal to pi times x to the 4.3. Okay. Yeah, so give it a shot. You know, why not? We're all here together. Let's try practice it and do what you think the power rule is telling you to do, and then go ahead and type in what you think it is into the chat box. That way, when I see what you think it is, in case there's any misunderstanding, it'll help me to understand where you might be stuck. Okay, so that's why I kind of want to see your answer before I write the answer on the board. What are you going to do with this 4.3 term? What do you think? I'm going to give you a minute to respond so that we can all start practicing. This is really nice. See, we're already practicing homework on a Tuesday now. So I know a lot of people during the Zoom sessions have said that they feel like they're always behind. But right now, honestly, if you're here and you're trying to take the derivative of this, you're actually ahead because we're already doing homework on a Tuesday. So bravo. So let's see what kind of things, what kind of ideas people have for the derivative f prime of x. Waiting to hear from you. Nice, exactly, right. Okay, good. So if you're looking at the chats there, exactly, what you do is the pi is just a constant multiple. So you're just gonna leave the pi alone. That's the constant multiple rule. Let's see, if you're holding the book right now on page 95, you'll see a thing that says constant multiple rule. And it says that if you have any constant in front, you just leave that constant alone. So is a pi, that's a constant in front, I'm just gonna carry that down, just like it says to do on page 95, okay? But then what we're trying to do is we're trying to take the derivative of this term. I put in parentheses so that you can see that we're focusing on this term. And then we're gonna do it in the same way that we did it with whole numbers. We're just gonna take the part at the front, the part that's in the exponent, and we're just gonna bring it down in front. And then we're gonna leave the x alone, and we're gonna raise x to a power that is 1 less than 4.3. And so 4.3 minus 1 is 3.3. So that's why we get 4.3 pi times x to the 3.3. Sometimes people might write that with the 4.3 in front. Just like before, I had written like, 2a times x instead of a times 2 times x. Whichever way you like it. That's the answer right there for the derivative. Excellent, great. So now you're really getting used to that rule there. And so what I want to do next is we're going to go to further exercise 2.5.4. 2.5 number 4. And we are going to apply this directly to a life sciences problem. So if you've had me in class before, you may have been with me for a week or two where I'm just waxing on poetic about power functions, because power functions are really prevalent, especially in biology, but also in the physical sciences and chemistry, and even some of the social sciences. Basically, wherever you see fractal structures emerge, you will see an associated power function. And so because in biology, we see so many fractal structures in the trees and the rivers and in the landscape, there's also power functions that are related to the descriptions of those fractal phenomena. That also applies to metabolic rate and body mass. And so here's a question right here. We're going to do further exercise 2.5 number 4. And in that exercise, it gives you this function that predicts an animal's metabolic rate as a function of its body mass. Usually, if you see this in a biology book, you would see this graphed on a log-log plot. And the reason that they choose to graph functions like this on a log-log plot is because it spans so many different orders of magnitude. So the fact that in further exercise 2.5.4, the fact that M, metabolic rate, is a function of B, body mass. This is true for a ton of different animals, like tiny little rats and bats and whatever else. It's true for them. It's true for humans. It's true for elephants. It's true for whales. It spans an enormous number of different animals, this relationship between metabolic rate and body mass. Okay, this is known as, I'm surprised he doesn't say this in the book, but this is known as, I don't know if I'm spelling it right, Kleber's law. It might be I before E, or maybe it's E before I, I'm not sure. But if you want to look this up on the internet, you can look up Kleber's law. And if you see that, you're going to see a graph that truly illustrates this with a bunch of different data points that talk about all the different animals that this is true about. Okay, but for our example here, it's going to say find the linear approximation to this function for a body mass of 100 grams. And if an animal weighs 100 grams and it evolves to weigh 110 grams, how much would its metabolic rate change? So this question is really related to all the things we've been learning so far in derivatives. I'm really glad that you brought this up. For part A, in order to find a linear approximation, we must first find the derivative, okay? So what we're gonna do here first is we're gonna find m prime. So practice again, and luckily we just got off of 2.5.10c, in which we had a fractional power, right? In 10c, this number up here was 3.3. Now, if you want to use the fact that 3/4 is equal to 0.75, and if you want to write this as b to the 0.75 instead, you're certainly free to do that, because 3/4 is the same thing as that. Because you know you're going to have to subtract 1, and so it might be easier in decimal form, or maybe you like to play with fractions. Either way, go ahead and use the power rule, and then you tell me what you got for the derivative. The m prime here, since b is the input variable, another way to say m prime would be to say d capital M db, d capital B, because the input variable is b. So the thing that the d whatever on the bottom is the input variable, the thing that we're taking the derivative with respect to. Okay, so the b is where the x usually is, okay? And the multiplier in front, that's just like the pi that we had in the previous problem. So you're just going to carry that down. You're just going to have a 0.8 right there. But what's the derivative of b to the 3/4? Just going to give you a minute to see if anybody wants to chime in on that. Okay, right? So we're going to carry down the 0.8. Now somebody has given me an answer that might have been simplified. I don't want to multiply this in my head, but yeah, right. So there's going to be something in the front, and then it's going to be b to some power. And what power is it? I'm actually getting a variety of different answers, which is good because it tells me that this is a sticking point for students. So I'm really glad that you asked this question so early in the week. So we're ahead of the game. Okay, let's go through this step by step. Hopefully everybody understands it's going to go down like that, right? But for the inside part, for B, we're going to carry the 3/4 down, and we're going to write B. And then the thing that's up here is going to be 3/4 minus 1, which is -1/4, exactly. So it's going to be -1/4 there. Right, right. Perfect. Yeah. So that's the derivative there. And then when we multiply 0.8 times 3/4, I suppose that's 0.6. So that's why people are responding with 0.6 b to the -1/4, or if you want to use decimal powers, 0.6 b to the -0.25. Yeah, either way you slice it, you have to subtract 1 when you're going down, when you're taking the derivative. You always subtract 1. This gets a little bit more confusing when you have a fraction up there, but you know what? You can type it into your calculator if you want to confirm. If you type in 3/4 minus 1, your calculator will say -1/4, just as a double check, okay? So that's the same thing that we did before. And then it says, find the linear approximation to the function for a body mass of 100 grams. Okay, do you remember that from the last section? Do you remember the section, actually not the last, but section 2.4, which was called linear approximation? So now we have to practice what we learned about linear approximation, because it says find the linear approximation to this function for a body mass of 100 grams. Oh boy, I think we can do it. I think we could. This is really good time to review that, because the concept that I'm about to review, the concept of linear approximation is the same thing that we learned in chapter 1 called Euler's method. Okay, so we always want to just take a step back and think about the big picture. Why are we going through all this? Why are we putting ourselves through the gauntlet of calculus? It's so that we can solve state equations. And what we learned in chapter 1 was that we are going to numerically integrate, or we're going to approximate trajectories. We're going to find the answers to the state equations by implementing Euler's method. And all Euler's method is it's a form of a linear approximation. Okay, so when it says to do linear approximation, we are actually sort of, in a way, implementing Euler's method. Okay, so it says linear approximation when the body mass is equal to 100. Okay, now what you need to know here is that for linear approximation, the first thing you need is the derivative. So check, we got the m prime. Okay, we got the derivative. The other thing you need is you need a point, right? Because this is the slope of a line. And what I'm trying to do right now is I'm trying to write the equation of the line. In order to write the equation of a line, I need the slope and I need a point. Okay, so what is a point on the function? Like when b is equal to 100, what is m equal to? So I need you to type that into the chat box. Hopefully a lot of you have calculators right now. What happens, what is m when I plug the number 100 into b? What is m of 100? Remember, m here is a function of b. So just use the same notation on both boards. I'm talking about m is a function of b. And now I'm talking about you plugging in the number 100 into that function and tell me what you get. That's one thing we need to know. And the other thing we need is the slope, remember? So we have a formula for what the slope is at any point b, but we also have to know exactly what that slope value is now when the point is 100. And so I want you to tell me what m of 100 is, but also what is the slope m prime at 100? Okay, and so that first part here is going to give you the point. And that second part, where you're evaluating m prime, is what's going to give you the slope. Good, you can read that. Point and slope, right? Okay, so just like you, I would really need to calculate that. And I see that somebody's writing. So I see some numbers coming up here, 25.3. I think that's probably the output from the function, right? 25.3, nice. So now we have a point on the line. I'm going to move this over a little so you can see more of the second board. Okay. So when I said point, what I really mean here is that the point literally is 100, 25.3. Right, that's a point on the line. And what's the slope at that time is going to be whatever m prime is evaluated at 100. And so what that means is you're going to plug in the number 100 right here. And you're going to do 0.6 times 100 to the negative 1/4 power. And is that where you got 0.189? It probably is, I'm guessing, because it looks like it, just eyeballing it, 0.1897. So I'm just going to approximate that. These are both approximations, I'm sure. This is approximately 0.19. Good, thank you. Yeah, 0.189 to be more specific, but I'll approximate at 0.9. So that's the slope. Okay, so when it tells me to do a linear approximation, all I have to do now is the same as if somebody said, I'm going to give you a point and a slope, and I want you to write the equation of the line for me using the point slope formula. So that's why there was a little bit of review, I think it was in section 2.4, about point slope formula, right? Is because one way we could write it is we could do m minus 25.3 is equal to slope times b minus 100. Okay, hopefully you understand what I wrote on the board right there, but I'm going to go back for review and help reference a page of where I got that, because you might be like, what the heck? Why did I put those numbers in exactly those places? And so I will ask you to go to page 83 for that. Okay, so if you're not really sure where I got this statement right here, go to page 83, and I'll just hold it up for a minute for everybody to see if you don't have your book. Do you see that form right there where it says y minus y naught is equal to the derivative evaluated at x naught times x minus x naught? That's linear approximation. That's me using the point slope formula with the point 100 comma 25.3 and the slope value of approximately 0.19, and there you go. That's what they're asking you to do when they say find the linear approximation to this function for a body mass of 100 grams. That's one form of the answer right there. Or if you want to get it into like the y is equal to mx plus b form, then you would solve this equation for m. And how you would solve this for m is you'd simply add 25.3 to both sides. And it looks like that's going to be m is equal to 0.19b. And then factoring this through, that's minus 19 plus 25.3. What's minus 19 plus 25.3? 6.3, right. And so these two terms combined on the end here would yield 6.3. So plus 6.3. So a lot of people like this this version of it better than that version, but that version is kind of easier to form when you literally have a point and the slope. You would just throw it into this point slope form that we saw on page 83. And then if you wanted to, you could get the slope intercept form by just simplifying it, just solving it for m on one side. And so what I'm saying is if a creature has a body mass of 100, this is approximately how their metabolic rate would change as you increase their body mass a little bit. Okay, and so the rest of the question says, use linear approximation to estimate how much it would change if we change from 100 up to 110. Okay. Just a second. I'm going to just move this over a little bit. Or actually, here, I'll just move it back because this board has better lighting. So to just finish off this problem now, I'll write down what I'm doing here. Okay, so use this to approximate m if b is equal to 110 instead of 100. Well, we just formed the equation, the linear approximation, and this is true for when b is equal to 100. And it's going to be approximately giving me the metabolic rate. If I plug in b is equal to 110, I'll get an approximation for what the function would actually be giving me if I evaluated the function at 110. Okay, so using this approximation here, so approximate m of 110 by plugging in 110 into the linear equation. And if somebody could please tell me what that's equal to. I don't see an answer yet, but somebody's telling me that m of 110 is 27.2. Okay, so somebody's telling me that m of 110 is equal to 27.2. That's what I got from the chat. Now, I want to say that there's two different ways. There's two different ways that you could get the metabolic rate of a creature with body weight 110. One way is you could approximate it by using this formula right here. Okay, so I'm just gonna plug in because I'm not sure if you plug that into the function or into the linear approximation to get that. So I'm just gonna confirm 0.19 times 110 plus 6.3, right, 27.2. Okay, good. Okay, so the approximation gives us 27.2, but now let me ask you a separate question. Okay, this is a linear approximation. That's what we approximately got. But now what if I just actually went back to the original statement? Because I did have the original statement that they're related by this. It's 0.8 times b to the 3/4. So let me see how close or how far away this approximation is to the actual evaluation by plugging in 110 into the original formula. So what if I did 0.8 and then I raised 110 to the 3/4 power? What would I get then? And somebody's telling me 27.2 also. And so that's not surprising because when we were doing all our calculations, remember when we rounded the slope to 0.19? The slope was actually like 0.1873 ... So because of the rounding error that I carried through when we approximated the slope, these two things are the same up to the 10th place in the decimal. But it's good in a way because it shows you that linear approximation. So this is the linear approximation. Approximation is 27.2. And this is the actual, that's the actual function, is also 27.2. So this is a good illustration of the fact that linear approximation does a good job of approximating an actual function. But what it doesn't do is it doesn't illustrate the fact that there is usually a little bit of error between them. And that would have been better illustrated had I not rounded it off so much. And somebody in the chat here is actually saying 27.1728. And so that, just keep that in mind, that these two things aren't exactly equal. It's just because I rounded that they came out very similar, but there's going to be just a little bit of difference. There's always just a little bit of difference between a linear approximation and the actual function. And now, to go back to the big picture of mathematical modeling, when we integrate state equations, when we do this process with Euler's method on state equations, the numerical solution that we get via Euler's method is going to be very similar to the actual trajectory, but it's going to be off by just a little bit. And we already learned that. And so I'm trying to tell you the same thing. And the reason that it's off by a little bit is a calculus-based reason. So they're really trying to revisit concepts that were built up in chapter 1, but seeing them in a more classical calculus format here. Okay, cool. So a little bit over time. Thanks for staying. Thanks for watching. I'm going to finish this session off by covering question 2.6.2 because that's kind of in line with what we were talking about when we were saying that integrals are derivatives backwards. Okay, so we're going to just do that one too. And I see a lot of people saying that this is really helpful to go through some of this stuff early in the week. And so, yes, thank you. Sure, you're welcome on my end, but also thank you. Thank you for being here, and thank you for contributing your questions and your thoughts, because teaching is an iterative process. It's not a one-way street. And so just hearing what your questions are is what allows me to be a good teacher for you. Okay, so I'm just going to finish today's session with 2.6.2, in which it says to find the antiderivative or integral of 3x squared. Okay, so that's one thing that I didn't stress enough, is that antiderivative is the integral. And so before, when I was saying that integrals are the opposite of derivatives, guess what? Another name for integrals is antiderivative, which kind of tells you it's like the opposite of derivative, okay? So that's all they're asking you for, is that they're telling you that the derivative is known to be 3x squared, and then they're saying, what's the original function? Where could that have possibly come from? And so for this, we have to do the integration process. We do the backwards of the power rule. The backwards of the power rule. And somebody else is saying, how do you integrate a function with fractional powers? So after I do this one, I'll actually do one more with fractional powers to answer that, and then we'll close out for the day. Okay, so you tell me, I don't know who's left here, but does anybody want to tell me this? We actually did exactly this one earlier in the session. So score one for retention. X cubed plus 3. Yes, yes, you remember. The 3 came from the fact that this was an x cubed, and the 3 hopped down in front. And then the 2 plus 1, because we're going backwards, is equal to the 3. And then for a really proper integral, don't forget that you have to say plus c. And actually, if you're paying close attention to your homework, exercise 2.6.1, right above the question that I'm doing, this is 2.6.2 right now. 2.6.1 says, why is the plus c necessary? So we already talked about this a little bit, but you know the answer. Huh? Yeah, remember you can rewind the live video later. And so you can see, you'll be able to answer 2.6.1 as well. Okay. Now, I know that was easy, and I mean easy-ish, because like the 3 was there and we knew that the 2 must have come from a 3, so that was very convenient. But let me show you a way that you can do this in more general forms where there might not be a 3 in front, and then it'll help me answer the question that was asked of how do you integrate functions with fractional powers? So we can use a trick I'm about to show you on that kind of question, okay? So now let's pretend that it wasn't a 3. Let's pretend it was just an x squared. Okay, this is a little more challenging. You tell me, what do you think if the derivative is x squared? It's not 3x squared, so there's no 3 in front. If the derivative is just x squared, what function did that come from? Where did that come from? I know there's going to be a plus c. Sure, there's going to be a plus c at the end, but x squared. So if x squared is the derivative, then I know it came from an x cubed, right? But the problem with that is that usually then I would expect there to be a 3 in front, but there's no 3 in front. Okay, so what you can do in general is that when they've given you a function here for the derivative and you want to know what the integral of it is, you want to take it backwards, you know you're going to have to add 1 to the exponent. So this is a general trick that's going to work on all power functions when you're trying to integrate them, is that you just take the function you had before and you just add 1 to the power, okay? So you're going to do x3 because you know there was, the 2 must have come from a 3, right? But when you take the derivative of this, a 3 would jump down and you don't see a 3 up there. And so after you've added the 1 to the power, you're going to divide out by exactly that same power. Okay, now let me show you why. The reason why is because when I take the derivative of this, having divided it out by the power that I just created is going to cancel itself. And that's exactly what I have there, is I have nothing in front, okay? So let me prove to you that this is the right answer by then taking the derivative again. And you see here I have a 1/3 in the front. And so I'm going to do the constant multiple rule. I'm going to have the 1/3 that was in front, right? And then the x cubed here. Actually, it might help if I write it like this, is what I was thinking. So what I was saying before is when you take the integral, you add 1 to the power, and then you multiply the term by 1 over the power. That's what I was trying to say. When I wrote it before as x cubed over 3, but it might be more helpful for you to see it as x cubed times 1/3. And the divided by thing is always meant to be exactly to cancel with that power. See, because then when I take the derivative here, I'm going to carry the 1/3 down, and this part is going to go 3x squared, right? And then the 1/3 and the 3 just cancel each other out, you see? Cancel, cancel, and so I just get x squared. Yeah. That trick is going to work every single time. So let me show you that trick again with a fractional power. That was a request of somebody. Okay, hopefully this part's okay. If you're confused about this, let me know in the chat and I'll try to explain away the confusion. But while I'm waiting to see if anybody has a question, I want to practice again with you. Let's practice one more time with a whole number, and then let's practice with a fraction. Like, what if I said the derivative was x to the 5? Now I want you to do the trick that I just did before, right? So x to the 5 is the derivative. And so where did the 5 come from? What is 1 more than 5, where it came down from? See if anybody wants to give an answer to this one. Maybe you had too much math today. I don't know. You might need to take a break. If the derivative is a 5 and we want to go backwards to where that came from, then it must have come from x to the 6, right? Because 5 plus 1 is 6. Right, exactly. And so then now that we know it's x to the 6, what we have to do there is we have to put something in front that's going to cancel out the 6. If I was going to take the derivative, the 6 would pop down, right? So I see somebody on there put 1/5. But what you actually want to do is once you figure out what this exponent will be, you're going to put 1 over that exponent. So you're going to do 1/6, not 1/5. And the reason that you do that becomes apparent when you go back and you check your work by taking the derivative. Because, oh, don't forget the plus theta. When you take the derivative and you go back down, the 6 is going to hop down, and then the 6 and the 1/6 are going to cancel each other. See, so that's why I put a 1/6. So when I take the derivative again, and I get the 6 to hop down, and I have x to the 5, the 6 and the 6 are going to cancel out. And then I'm just going to get x to the 5th. Okay? Do this trick, and you go 1 up on here. Whatever number you put up here for the antiderivative or integral, you would also put it 1 over that same amount right there in front, so it'll cancel out. And now we'll do one more, but we'll use a fractional power instead of a whole number power. Okay. So now instead of that, let's say, oh, I don't know, how about 2/3? Let's say that we know the derivative is x to the 2/3. And if we want to do antiderivative, it means that we have to do 2/3 and we have to add 1. Add 1 to that fraction. So what's 2/3 plus 1? I want to see what do you think the answer is? Because when we take the antiderivative, we have to go back up. So we have to add 1 to it. Sometimes it might be helpful for you to do a little scratch work over on the side. So here's my little scratch work bubble. I need to know what 2/3 plus 1 is. So what's 2/3 plus 1? Sometimes, just to review for fractions and stuff, you would want to change the 1 to a 3/3 so that they have a common denominator, and then you would get 5/3. Right, right. So then when we go from derivative and integrate up to the original function, we're going to have x to the 5/3. The power is going to be 5/3. Okay, exactly. But what do I have to put in front of the 5/3 so that if I check my work by taking the derivative, I'll get them to cancel out because the coefficient in front is just a 1. Same thing I was saying before. You're going to do 1 over whatever it is you just put in the exponent. So I'm going to do 1 over 5/3. Ew, fraction over fraction. But luckily, you're at the level where you can handle that now. You're used to that. And so 1 over 5/3, exactly what you're saying there on the poles, is 3/5. Right, so you just invert the fraction. And then, oh, my bad. That's F. So I'm just simplifying the 5/3 here, and I'm writing 3/5 F to the 5/3, and then a fall of 3/5 coming down, and then the 5/3 coming down from the x, and then 5/3 minus 1 is 2/3, right? And so cancel, cancel, so then you get the x to the 2/3 that you had before. Of course, when we integrate, there's always a plus c, so technically there should be a plus c on those two lines. But I hope that this really helps to have you understand the power rule better. It's actually good to go from function to derivative and then from derivative to function so that you can see that when you go back up, when you integrate and you go back up, you add 1 to the power. And when you take the derivative and you go down, that's the power rule. So you subtract 1 from the power. Okay, cool. You did a lot of math today. You did some good work breaking out the exercise sets, and so I hope that really helped everybody. Thanks for sticking it out. This is kind of a long session, but as long as it's helpful to you, then I'm really happy to be here for you. So thanks for joining me, and I'll see you next time.